Okay, so at last we saw each other, we were discussing a specific type of vector field, which we labeled a conservative vector field. And in fact, the majority of the vector fields that are of interest to scientists and engineers are indeed conservative vector fields. One of the important geometric properties of conservative vector fields is that they have vectors that are normal, that are perpendicular to level curves. So clearly, if conservative vector fields are of interest, we need a way of being able to find out if you're given, say, a vector field like this, to be able to tell if it is a conservative vector field. So we're going to start with a very short test. And the way the test works is, so this is the part that you're going to be given. You're going to be given some vector field. So for example, in part A, part B, you're given two different vector fields. And whatever component is attached to I, we're just going to label that M. Whatever component is attached to J, we're going to label that N. And the way the test works is the partial of N with respect to X should equal the partial of M with respect to Y. And if they do indeed equal each other, then we will make the statement that our vector field is a conservative vector field. So this is not a proof-based calculus class, but I have provided the proof for why this test does work if you care to inquire. But let's go ahead and use the test, right? So I have, my apologies. So I have, go ahead and erase this. Believe it or not, I've actually already recorded this video. Then for some strange reason, I never pressed record, or I pressed record and pressed stop recording at the same time. I don't know, but the video is not there. I call conspiracy. Ready? So here we go. So I'm going to go ahead and label M and N, and I'm about to take some partials, but let's go ahead, and it might even be worth writing. M is equal to x squared y. N is equal to xy. All right, so the thing that you have to just be mindful of is that we want to take the derivative of n with respect to x, the derivative of m with respect to y, and that is important that we don't mix those up. I've even done it myself. At times. So we want to take the partial of m with respect to y. We want to take the partial of n with respect to x. This is the way it's going to work. So ready? So if you take the partial of m with respect to y, well, you're just going to get x squared. If you take the partial of n with respect to x, you're going to get y. So clearly these do not equal each other, right? Clearly these do not equal. So we want to now make a statement that this is not a conservative vector field. So I understand that a lot of students will perform work like this and they'll stop without ever making the statement. They'll never draw the conclusion. But you are leaving it up to me to assume that you know that this is not conservative, right? It's the equivalent of this is you arguing, and this is you saying therefore conclusion. If you have no therefore conclusion, then you've just wasted a whole lot of time arguing, right? Without drawing a conclusion. So please conclude. Let's go ahead and do the same thing here. So we got partial of m with respect to y, partial of n with respect to x. And in this case, if you take the partial of m with respect to a y variable, that just is 0. If you take the partial of n with respect to an x variable, that's 0. So in this case, they do equal each other, and thus, yeah, f, your vector field, is conservative. Okay. So at this stage of the game, we have a way of being able to tell if a vector field is conservative, but that's clearly not good enough, right? If conservative vector fields are of interest, then we're going to want to go a little bit farther. So let's go back to what it would mean to be a conservative vector field, right? So let me make this a little bit larger here. So this is kind of calling on the tail end of the last video. The idea is that if your vector field is conservative, so here's your vector field. If it is conservative, then there is some function out there. We don't know what it is, but there's some function out there such that if you took the gradient of that function, the vector field would be equal to the gradient of that function. Okay? So the goal is to be able to find what function that is. So the goal is we want to be able to make the statement f of xy equals, and now we want to be able to fill that in. So let's start with here's our vector field. Before we start going through a bunch of mathematics of trying to figure out what the function, the potential function of this is, let's first make sure that it is a conservative vector field by applying our test, right? So in this case, if you were to take your partial of m with respect to y, so labeling m, labeling n. So if you take your partial of m with respect to y, you get 2x. And now if you move to the partial of n with respect to x, you would also get 2x. So it does meet the criteria to be labeled a conservative vector field. So now how do we go from here? So let's make sure you understand. So here is our definition. Of a conservative vector field. If a vector field is conservative, then there is some function out there such that the gradient of that function is equal to the vector field. All right, so the gradient of that function is equal to that vector field. So hold on for a second, just make sure you understand. Do you understand? We know this part, right? So I can, and I will in just a second, take this and substitute it in. So let me go ahead and do that right now. So the vector field that we are given is 2xy I direction plus x squared minus y in j direction. Now this has to equal the gradient of some function, and the function is what we're trying to figure out what it is. Well, come walk back in time with me. When you take a gradient, right? If I give you a function and I ask you to find the gradient, do you remember you would take the partial? Take the partial with respect to x, take the partial with respect to y, and then you would simply attach the partial with respect to x. You would attach it in the I to the I component. the f partial with respect to y in the j component, and that would form the gradient. So does it not make sense that we have the partial derivatives, right? If you took the derivative of this function out there, if we took the partials with respect to x and y, we already have that part. What we don't have is what we took the derivative of. We don't have the original function. Well, you know what to do. If you have a derivative and you want to go back, we need to integrate. And that is exactly what we're going to do. So I'm going to go ahead and make the statement, although I believe that you see what I'm trying to state here, but I'm going to go ahead and make the statement that the partial with respect to x is 2xy. The partial with respect to y is x squared minus y. I need to figure out what I took the derivative of. So I need to integrate. So I want to integrate 2xy. I want to integrate x squared minus y. Now, obviously, if I took the derivative with respect to x, I want to integrate with respect to x. Likewise, if I took the derivative with respect to a y, I want to integrate with respect to a y. So this is fairly easy. We're just going to go ahead and a fairly easy integration. So we're going to integrate with respect to x, so that's just going to be x squared y plus, now here's where we have our constant of integration. I'm going to, I'll use g. And just remember that for multivariable functions, your constant is itself a function. In this case, it'd be a function of y. Right? Your constant of integration is itself a function. It's not a multivariable function, but it's a function. Nonetheless, let me continue here. So if I integrate with respect to y, I would get x squared y. Now if I integrate negative y with respect to y, I get negative y squared over 2. And then I need another constant of integration. I'll just use h. This one would be a function of x. Okay, so now if I haven't lost you already, if you will listen to me right now, I can save you some time. I have to speak somewhat informally to do so, but I can definitely save you some time. I remember the goal is to find that potential function f. So the question is, how do I use this information to form f? So let me talk out loud as if I were doing this on a test. Okay? So let me start with this first part. So I would state, okay, let me go ahead and take this x squared y. I don't have one of those. I'll go ahead and take that plus g of y. I don't have one of those. Then I'll come down to the next result from the integration, I'll say, well, wait a minute, I have an x squared y. I already have one of those. I don't need another one. But I don't have a minus y squared over 2, and I don't have that h of x. I'll take that. And what I'm trying to tell you is that for the purposes of your test, you can give this as your answer. Let me also, while I'm here, go ahead and state that, or tell you that if you were to look the answer up to a question like this in the back of the book, it would not look like what I've written down at the bottom. Instead, it would look something, if you looked it up in the back of the book, it might look something like this. And really what's happening is they're just doing some a little bit of manipulation to clean it up. I mean, they're saying like let h of x be represented by some constant k, and g of y can be represented by negative y squared over 2. So do you see how they're just doing some manipulation to write a cleaner product, but they haven't added anything of it's cleaner, but they haven't added anything of value by doing so. Let's do me a favor now. Let's fast forward. Let's assume that you're taking your test and you start to second guess whether this is right. Well, look, take the gradient. You should get this vector field. That's how you know that you're on the right track, okay? And remember, when you take the partials, these zero out regardless. You can also do it from here. You can prove that it is equal to f, capital F, vector field. All right, I know you're getting a little tired, and since I have actually taught this lesson 2 times in a row, this is my second time because I guess I didn't press record, and if it's a third time, then I'm just throwing this iPad out the window. What we're going to do is I need to tell you where we're going. So the idea is we want to use this knowledge of conservative vector fields, but we need to extend it to space, right? Beyond 2D into 3D. And in order to do that, we're going to need a test, right? How do we, what is the test for figuring out if so here, notice now my vector field is in space. So I would need a test to be able to figure out if it's conservative. And then obviously I also am going to eventually want to be able to find the potential function out there. So, but to build, in order to introduce the test, I need to introduce a concept of what we call a curl of a vector field. And so if you, in your section 15.1, they do not give a geometric interpretation of the curl yet. Okay, this is the geometric interpretation of a curl for a vector field comes a little bit later. But I don't really want to just start doing a bunch of analytical work without telling you, at least geometrically, what it is you're trying to do. So let me just kind of tell you. So the curl of a vector field, it informally just measures the rate of rotation at each point. So curls measure the rate of rotation at each point in the vector field. If you end up with a curl of 0, we would say that it is irrotational, meaning the vector field is irrotational. The vector field has no rotation, is what they're stating. And how do we find the curl? Because we're going to need the curl to be able to do the test. So to find the curl of a vector field, you're going to make use of a cross product. And this is kind of, well, I'll do my best. I'll do my best to try to explain what's happening here. But it's the cross product of the vector field with what? Well, so what's happening is they're using the cross product of a gradient of f, and they're treating it as a differential operator, right? So the gradient of f is a differential operator that is acting on f, is basically what's happening. But I don't think we need to spend a lot of time there. Here's the deal. So if you want to find the curl, how do you set up your cross product? Well, your cross product is set up just like this. Okay, so the m, the n, the p, that is going to be given to you, and you're going to need you're going to need to set up some partials. In fact, you're going to end up taking quite a lot of partials if you look at it in order to get your curl. Finally, if your curl is equal to 0, then it's irrotational. So when we return, we will find the curl of this vector field.